variety class. We're going to get started here this evening. Let me, before I introduce our speaker for this evening, let's have a word of prayer, shall we? Let's pray. Father, we thank you for this wonderful evening. We thank you, Lord, for the opportunity to be here, to learn something about the multiverse, the string theory that Dr. Cleaver has been studying for many years now. And I pray that you would bless our time together, anoint this time, Lord, may this be time well spent for everyone, and we ask that you bless Dr. Cleaver in this time with us as well. Father, we just thank you and we praise you now. In Jesus' name we pray. Amen.
Amen.
All one. We've had the privilege to know Dr. Gerald Cleaver for a number of years. He is professor of physics and graduate program director at Baylor University, just 3 to 4 hours down the road, depending on the traffic. And Dr. Cleaver got his BS in physics and mathematics at Valparaiso University, and then his master's and PhD in physics at Caltech University. He is a fellow of the American Scientific Affiliation, and that's the first time that Dr. DeBoer and I met. Dr. Cleaver was at an annual ASA meeting, 2009.
I think so.
At Baylor, when they hosted it. And that's when we first heard Dr. Cleaver speak, and we thought, oh, we've got to get this string theorist to come up here to Laterno and talk to our students about it. And so he's been here before, but not when any of you were students here. I think it's been about 5 years since the last time he's been here. Anyway, he's a string theorist, and there's only around, 300 of those?
Something like that.
In the world. And so he's one of those rare string theorists. He's also the head of the Early Universe, Cosmology, and String Theory Division of Baylor Center for Astrophysics. And so he has over 80 peer-reviewed journal papers and over 1,300 citations on those. So this man is well known in the physics community, and he's also known amongst Christians who have been trying to ponder this multiverse idea. So let's give a warm welcome to Dr. Cleaver.
Thank you all, and just sit back. I'm going to try to string you along for the next hour. Okay. And I'm going to focus on the multiverse. And this is one of the very interesting implications of string M theory. I'm going to say string M, but let me clarify one part. String theory was the name of the research that I was in for about the first 10 years, from its origin in the mid-'80s to about 1995, and then there was an advancement in it. The fundamental particle in nature was believed to be a one-dimensional string, and then it was realized it had some thickness, becoming two-dimensional. So at that point, a string started to be we started calling it a membrane instead. So string theory flows nicely, membrane theory does not. So membrane theory was simply shortened to M theory. But it's the same thing. Whether I say string theory, now I mean the present form of it, which is M theory. So sometimes we just say string M, and if we just say string, it's the same thing. So what I'm talking about it. But one of the, as I said, the basic profound implications of string theory now is that the universe that we live in is not all that there is. That creation is much more vast than we've ever imagined before. And what I'm going to go through, what I'm going to start with, before I get into multiverse itself, is just review basically the history of what I will call the paradigms of reality that humankind as a whole perceived. And I'll show with the advancements of the 20th and now 21st century how the present view that we have, what I would call universe-centric view of reality, is becoming and strongly suggesting a multiverse-centric or multiverse perception of reality. And we'll see why we think that is so within cosmology and theoretical physics. And it's not just implied by string theory. Overall, many evidences in cosmology are applying it, but since string is my field, I will focus on that. But I'll give a broad view also of the general reasons why we suspect that we may indeed exist in a multiverse theory. And what do I mean by multiverse? Basically, I mean a vast collection of universes. Some perhaps like ours, but most likely the vast majority vastly different. The specific type of multiverse that comes about depends on the particular theory. Like string theory predicts a multiverse with certain features, such as I'll get to, somewhere around 10 to the 500 different physically distinct universes. That means the physical laws differ significantly in something on 10 to the 500. And what's that number really? Again, imagine a 1 with something around 500 zeros after it. That's not an exact number, but string theory suggests that there's somewhere between 10 to the 100 and 10 to the 1,000. So we just use the geometric mean of that and average it to 10 to the 500. We can't give an exact. But that's basically what I'm going to cover. I'm going to skip a few of these slides to get out of here. I'm going to go back to basically take a look and think of, in essence, I think the first organized paradigm of creation, and that is, I think, what we would call sometimes the three-tier paradigm of the ancient Mideast world. And that was essentially from prehistory to about 300 BC, in some areas of the Mideast, to about 1st century AD in others. And this is the understanding and perception of reality that is discussed in the stories in Genesis, of the creation stories. And that this was a view that people in the Mideast perceived it was a phenomenological view, looking around the local area. And what could they see? The sky, the land, and the underneath. And this essentially became known as the three-tier paradigm because it had, just like we see there, the earth and the flat area. There was waters, the oceans, the vast lakes, and that was perceived to be what surrounded the land. And there was, of course, the land of the dead, the underworld, that all of the Mideastern societies perceived. And essentially the earth, the land, was thought to be a floating mass on the lower waters. And there was also the firmament of the stars high in the sky, and the oceans of heaven. And this is in Genesis where they talk of the separation of the waters. This was because there was a perception of waters in the skies, and it was holes in the firmament that allowed the rain to come down then. And that was the perception of that. And then the heavens of the heavens, where we would perceive God, and the Greeks did of theirs also. And again, this was around for quite a while, but then it was actually the Greeks that around by the time of 300 BC were from astronomical observation and also the philosophical sciences that were beginning with Aristotle and all. They were beginning to realize, and they had good evidence, that the earth was, in fact, a sphere. And some of them were, in fact, able to compute just from the curvature within local cities in Greece. They were able to actually estimate what the circumference and radius of the earth were. And depending upon whether the measure of their, what was called a statum, whether it was exactly whether they were using the Greek or the Egyptian version of it, they were within, as close to, in their estimates of the radius of the earth, within 3% accuracy, which was very good. You don't imagine that. They did. And the largest uncertainty, if they went with the Egyptian unit of measure, was only 11% off. So they were somewhere between 3 to 11% accuracy, just by measuring what the curvature was in the land between two Greek cities. And that's amazing that they could actually do it that well. And then they perceived, with the Earth the center, and that's why we call it the geocentric paradigm, that all of the moon and the planets that they could observe, which back then was just Mercury, Venus, Mars, Jupiter, Saturn, and then the sun, in those orders, orbited around the Earth. And that was the dominant view. That was the longest lasting quasi-scientific understanding of the reality of our of existence. The longest stage that we've been in. And that was, again, from Greco-Roman to the 1600s. So that was almost, for 2,000 years, that was the perception of what reality was, at least as we could see it. Then we went through the heliocentric paradigm for about 100 to 200 years. And this was, again, based on observation, starting with Copernicus and then Galileo, and the idea, and then confirmed by Newtonian physics, the idea that the sun was the center of our solar system, not the Earth. And you all know about the significant paradigm shift that Europe went through and then spread to the rest of the world in the 16 to 1700s. But still, even in this sense, the stars were just seen as distant possible clouds of gas. Some people did perceive that the stars in the sky were very likely suns, just like ours, and those had planets too. And in fact, in the Mideast, that was theorized as early as about 1200. And then, of course, there were some in Europe too, by 1600s. But that still, it was a vague perception of what the stars were. So really, up until through the 1700s, I'm just going to call it the heliocentric paradigm. The sun was really thought to be the center of creation. Until then, basically by the 1800s through the 1920s, we did develop and advance to what I'll call the galactocentric paradigm. It was realized that our star, our sun, was not that different from the rest of the stars, and that the rest of the stars that we were observing formed a vast galaxy. And it had been realized that the cloud, the milky cloud in the sky, was in fact formed from a vast number of stars, very dense and packed along the center plane of the galaxy. But even the surprising thing was, even through the 1920s, even Einstein, when he was developing gravity, thought that the entire universe was formed, existed only within our galaxy, that there was really nothing beyond it. And that's amazing. You know, our galaxy is about 100,000 light years in diameter, and about 10,000 in thickness in the center, in the core. And that basically was perceived to be everything. There were these gaseous clouds called nebula, and they were assumed to be gaseous hot clouds of hydrogen or helium gas, but existing within our own universe. With our own galaxy. Some people had suggested that these might indeed be very distant galaxies just like ours. But it really was not until the advancement of telescopes in the 1920s that specifically people like Hubble could look at these and identify them as individual galaxies. And even up until that, he did not come out with that until 1925. There was a great debate around, I think it was 1922, on whether the nebula were indeed just gaseous clouds within our galaxy, or they were distant. But it was, there was strong support for both sides among physicists and astronomers at the time. But it really was not until there was empirical evidence from Hubble's observations that it was realized that ours was not the only galaxy, that it was not simply a galactocentric paradigm. And we advanced then into what I would say now is the universe-centric picture. And this is a computer simulation. It is not a real picture of the universe, believe it or not. But here, each individual dot is its own galaxy. And this is a computer simulation of observable patterns. There are somewhere around 1 trillion galaxies. Actually, closer approximation is about 300,000 observed galaxies, and up to about 0.5 trillion to 1 trillion stars in the largest type galaxies. So the universe is very, very vast. We know that it's about 13.8 billion years old, and the observable region, what we're seeing now, what we could see because it emitted light, basically 14 billion years ago. The distance that the furthest away galaxies are from ours now is about 14 billion. You'd think, okay, let's just double that. They were 13 billion light years away when they were shown that we're seeing now, and they're traveling approximately at the speed of light. So you basically double that. But there's also the speed at which the universe is growing, and I'll discuss that, has been changing. It's been accelerating. So the actual size of it is more than just 14 billion light years times 2. It is indeed closer to about a little bit over 40 billion light years in any given direction, in terms of the galaxies that we see now, where are they? So it's saying what we'll call the observable universe is at least 14 billion light years in diameter in any given direction that you look in. And so this is the picture that we have been in, and basically are in, I'll say, from the universe-centric picture from the 1920s to the 21st century. But then what I'm going to suggest in the rest of the talk is that we are on the stage where we are leaving the universe-centric picture. And we're going to look at the history of the universe to see what happens, what has happened, what's leading us into what I believe is the multiverse-centric picture. It should have multiverse-centric picture, not of universe, but it should say multiverse-centric picture of reality. Saying all that there is, we are just one of a vast number of galaxies, of universes. And we're going to look at some of the evidence of that by going back and looking at some of the physics that we know about our own universe. And the history of the universe, it is well understood. You know, the 14 billion years, you can't just look at what happened, say, 12.5 billion years ago right here, but overall we do know the general history, the general primary events within the history of the universe, back to, in fact, a fraction of a second after the Big Bang. And when we're trying to study, you know, the current state of affairs involving whether there is or is not a multiverse, we're actually going back to studying the universe and theorizing about it in the stage that it was in prior to 10 to the minus 40th of a second of existence of the universe. And that's getting back really close. But again, we do understand it really well, both from a large scale, what we're looking at now, to a very, very small scale. And what we've seen is a very interesting pattern, very, very interesting characteristics, some of which we understand, some we cannot really have another good explanation for unless our universe is just one of many. And we'll start, basically, we know where we are now. And the universe has gone through various stages. It starts off in about the time 0 to about 10 to the minus 43 seconds. We call that the Planck epoch. At about that time, at the end of the Planck epoch, the universe itself had a size of about 10 to the minus 33 centimeters. And that's a significant size because that's really the smallest length of anything that we can really understand at which distance has any meaning itself. Smaller than that, quantum mechanics and quantum gravity take over, and space-time is basically an indistinguishable thing. There's no real clear distinction. You can't really measure anything until you get at least 10 to the minus 33 centimeters or larger. And sometime during both the Planck epoch and this, when it was up to about the string scale, or the Planck scale in length, it went through this inflationary stage. We know the basic physics that was producing it, but the cause of the basic physics is not understood well. The basic proposals that are being looked over, what caused this inflationary stage. And what do we mean by inflationary? Inflationary stage was, again, when the universe was no smaller than 10 to the 33 centimeters, and then with about the same time scale of about 10 to the minus 33, 32 seconds, grew to about the size, what was small, grew to about the size of a basketball or soccer ball. It grew extremely fast, significantly faster than the speed of light itself. That might seem contradictory to what you know. You know things cannot travel faster than the speed of light. Things can't, but space itself can. And we know that happened. There's overwhelming evidence for it. And if we go and that's one rule. I'll bring that up a little bit later for some other issues. But again, realize that space itself can travel faster than the speed of light. There's no absolute limit to the speed at which space can expand, given that it has enough energy. And this is one of the variables that we'll see predicted in the multiverse, that our particular value of the expansion rate now and inflation then may have been particular to our particular universe. Because it's a very low probability condition for the specific values that we had, but when you have a general multiverse theory, you have a vast range of both inflation and later acceleration values. After we went through this inflation, then we were at what was known as a grand unified theory, and this was about 10 to the minus 43 to 10 to the minus 36 seconds. And it was at this stage that all of the forces that we know of acted together. I should say the non-gravitational forces. Electromagnetics and the strong and weak nuclear were acting as the same single force. That's why we call it a grand unified. All the forces were unified together. What we see is, and what happens when we study the forces, when we combine them with quantum mechanics, we see that the strength of the forces and their properties actually change depending upon the overall temperature of the universe. And the universe, when it was very, very young, was extremely hot. And as it expanded, it cooled. Matter and energy was spread out. It wasn't interacting as much. So just like in a fire, if you spread out the ashes and the burning wood, the overall temperature of the whole thing lowers. And same thing, that's just a classical analogy for what happened with the universe itself. As it grew, it cooled. And essentially, the temperature of the universe was inversely proportional to the overall size that you measure. So the universe doubles in size, its temperature cuts by half. Is a fair rule, and that's independent of the number of dimensions that spatial that a universe has. And so when it was hot enough, the conditions were right that all of the forces acted the same. But then as it got cooler, the strong force separated from the electro and weak forces. They were still combined, so we called them the electro-weak, but at the stage of 10 to the minus 36 to 10 to the minus 12 seconds, we had strong nuclear force and the electro-weak combined force. And then, when it was around 10 to the minus 12 to 10 to the minus 6 seconds, the electro-weak, the electromagnetics and the weak nuclear force themselves separated. And so, by the time we got down to about 10 to the minus 6 seconds, all of the forces had broken up. The strong was separate, the weak nuclear force was separate, and electromagnetics had broken off. And another way of thinking about this is when the forces broke, they broke because the particles that are responsible for forces, like electromagnetics, is the photon. Strong force has things called gluons. The weak force has things called the W and the Z particles. They became different and distinct. And what happened for the electro-weak is that the W's and the Z's and the photons separated because 3 out of 4 of those particles became massive and only the photon remained massless. And again, this was an effect of the changing temperature and how the forces changed and varied. When the temperature got cool, some of the particles ended up coupling to a particle called the Higgs, which you may have read was finally discovered at CERN last year. And that basically confirmed that our understanding with the discovery of the Higgs particle, our process for understanding all of this is very accurate and has to be right. We would not have been able to predict the Higgs without if this had not been right. And the Higgs is an interesting particle too. It's basically like a glue, but it's stickier to some particles than others. And the more massive a particle is, that basically the Higgs sticks to it more and slows it down more. And so it takes more energy to make it go faster, to just get rid of how it interacts with the Higgs. And that's now the explanation of mass, is because the Higgs exists. If the Higgs didn't exist, the Higgs field and its particle, everything would be massless and traveling at the speed of light. We could not be sitting here talking. So we should be very thankful for the Higgs. And actually, the Higgs was named after one of the discoverers of it, and that was about the shortest sounding of the set of all 6 of them. So they just called it that. But when it was awarded in Sweden, they did announce all 6 names of the discoverers of it. And, so there's not a bias seen in that. Then we went through various stages. And each of the primary stages were determining how, after this inflationary stage, how fast the universe as a whole was going to be expanding. We went through a stage where most of the particles were photons or the neutrinos. Basically everything, the dominant particles were the photons, and they were essentially traveling at the speed of light. They were just basically like radiation, so it's known as the radiation-dominated era. And that controls the physics during that stage. And at that stage, the universe was growing at about half the speed of light. That's based on what the energy density was and the function of these photons to basically push space out. After that, we were in the matter stage, and up until 1997, we thought we were still in the matter stage. That's saying that particles are the dominant thing, the dominant energy around. And when that happens, they're still pushing and causing the universe to expand, but at a rate of about 2/3 the speed of light instead. Then we actually discovered that weird thing is the universe is not going at what we thought was probably a constant speed, or actually gravity countering the massive particles and everything, possibly slowing down, but the universe is accelerating. It's growing faster. That means the universe is expanding faster right now than when you woke up this morning. You probably tell the difference and everything. But no. Actually, around galaxies, there's enough matter that that space really doesn't expand. The gravitational effect of galaxies keeps that from happening. But in the empty areas between galaxies is where the universe expands. And it really is. There's been a significant expansion between now and this morning in spots between galaxies. And that is one thing that we really can't explain, and I'll get to. We really can't explain it because it was always figured that if we just normalize to 1, about the strongest acceleration we could have, and we call it 0, no acceleration, it was thought that, we look at the physics, and if it's going to be accelerating, we could understand why it would be probably full speed, on full acceleration, unit 1. Or not at all 0, but instead the acceleration corresponds to an energy producing it that has a value of 10 to the minus 120. It's not 0, it's very close to it, and it's not 1. So there's been really no real explanation for it. And this is one big question that I'll get to. One of the sciences that we know it well, we know what it is, but we really can't explain it. And this is one of the big questions. If you ask one of the significant questions in physics and cosmology right now, that's probably the biggest of all. Why the acceleration right as it is? Why the corresponding energy density in the universe? Why? And it's called the cosmological constant, or sometimes dark energy. It's all the same thing. But why 10 to the minus 120 rather than 0 or 1? I can't answer it, but string theory thinks it can. And so we'll look at that. Let's see. We've also taken a look, again, support of this whole history that I've reviewed can be seen in the cosmic microwave background. And this is the light that, as it was at 300,000 years after creation, when the universe cooled enough that that electrons were slow enough that they could be captured electromagnetically by protons and neutrons to form full atoms. And at that point, light that had otherwise could only travel less than a millimeter before it went from proton to electron and everything could escape, and it was free. And we see all of this now in the cosmic microwave background. It was hot. As I said, the universe cools, it gets cooler. It was trillions of degrees when it separated, and now in terms of the temperature, it's almost absolute 0. It's about 2.7 degrees Kelvin. That is in Kelvin degrees above absolute 0. But there's some slight variations, and that's what you see in the CMB. And it's that slight variation, and the red is the hotter and the blue is the cooler. It was those slight variations in the photons. That meant where they were hotter, there was more matter. Where they were cooler, there was less. This was the fundamental difference in energy distribution that allowed galaxies to form. It was this sort of fine-tuning. The temperature variations, it's 2.73 degrees, but the variation of that is 1 part in 10 to the 5th. And that is the distribution in here that allowed galaxies, because it was that fine-tuned again. And the explanation for that, why the conditions were like that at the beginning of the universe, are not understood either. Well, we just know that they are. And again, this is just simulating what I said. The universe we now know is accelerating in size, not just at that fraction of a second after the Big Bang, but now it's growing faster and faster. Very, very slow compared to the speed of light, but nevertheless it is. And all of these things, the basic explanation for why we can have a universe with the properties that it does, all of them that are very improbable on their own, are it makes sense that they can be probabilistically explained through the multiverse picture. That there are various universes that have different properties randomly distributed, including things like the dark energy value, the initial temperature, things like that, the temperature variations. And string theory has a scientific explanation and prediction of this. And it predicts that there would indeed be a large number of universes with differing properties. Again, like I said, that there would be somewhere around 10 to the 500 different universes with different properties. And that makes sense. And that fits the parameters. We need it in order to have the cosmological constant at the small value that we do at 1 part at 10 to the minus 120. That says that there has to be at least 10 to the 120 different universes with that varying in cosmological value that will hit, and that way they would be spaced in parts of 1 part in 10 to the minus 120 for the cosmological constant distributions. And so our number fits good. String theory predicting somewhere between 10 to the 100 to 10 to the 1,000, the minimum value that basically we need for the cosmological constant to be as small as ours is 10 to the 120 different universes. And so I want to talk about also not just the string theory what a multiverse is, because it has specific properties, but it's well enough predicted and understood that it's there's a good likelihood that it's not just our universe, that cosmologists are defining classes of multiverses. They're known as levels, and one of the leading people in this field is Max Tegmark at the University of Chicago, and he has defined the 4 classes of multiverse. And the way he classifies them, the simplest is level 1, then level 2, level 3, and then level 4. And he's done it a lot like, sort of in parallel to the taxonomy of the biological taxonomies. Like the largest kingdom, phylum, class, order, family, genus, species, the most specific. A genus contains all of species within it, like that. And his 4 levels work like that too. A level 1 multiverse is a lot like ours, and ours would be the universe that we're in would fit as a level 1 multiverse if we first off realize that our universe probably does not stop at the observable limits that we've seen. Why? I mean, there's good evidence just as we look around. The physics that we see in our universe is constant. And there's a random, you saw that computer-generated slide that I showed a little bit earlier, there's a random distribution of matter throughout the universe. Galaxy here, galaxy there, a distribution of galaxies. And it doesn't just stop at some point, and we can see, well, the laws of physics are good here, and they've shifted here. It's clear throughout the observable universe. And if we could go to the edge of what we can see right now, and we could look on further, we probably wouldn't see any change in the universe beyond. Because if we can move further away from us, then the distance that we could actually see would again be about 13.8 billion light years away, but it would go further out. So there's not just some boundary that we can see to our universe. It likely goes on and on and on, and possibly infinite for our universe itself. And this is what defines a level 1 multiverse, a universe of infinite size. And one of the interesting things then that Max Tegmark is somewhat of a philosopher too. He actually goes in and considers, okay, we have a level 1 multiverse, and a level 1 multiverse is also defined as saying that it is that region of connected space in which the laws of physics are all the same. And basically that it's going to be vast and perhaps infinite. He's done some probability examinations of how far away does something have do you have to go to find objects reproducing themselves. Example, like, there's only so many fundamental particles of matter. And if you consider a given volume, how many different ways can matter interact or produce different objects within the closed area? For example, just let's say a cubic meter, and you put in some number of atoms. How many different ways can those atoms form in that area? It's going to be a finite number. And so he says, okay, if there's a finite distribution of that, how far away would you have to go in this universe to find that identical object again? He's working on he's thinking on the larger scale. For example, like, how far away would we need to go to find a star that's exactly like ours, or a solar system that looks exactly like ours, or a galaxy that matches? It's an identical sibling or identical twin for the Milky Way, and he computes all of these things, and it gets interesting because basically he's computed the probabilities for finding a planet like Earth, and in which we are a copy of us, physical copy. And he could actually tell you based on just general probabilistic distribution. He doesn't consider anything such as individual spirits of our own, and that we each the body of soul that would distinguish us from another twin. But he's computed, and it's interesting if you read some of his papers on that, on how far away you have to go to find a double-ganger of any given object, even of ourselves. But again, I don't have any problem with that, although it seems it's probably far-fetched, because it's really no different if someone else, such as me, was talking. He might have chosen to wear a different shirt or something, or coat color or something, but it would still, to me, it would be no different than myself having a twin, or triplets, or quadruplets, or whatever. They're still individual beings. So there's been a lot of philosophical books and papers written on that idea, both pro and con. But nevertheless, I think it's interesting reading, but I don't think we need to be afraid of it. Level 2 multiverse is what string theory would produce, because level 2 is a collection of level 1 universes. Each level 1 universe has its own set of physical laws. And so there's our universe in a level 2 universe, and this other set, such as string theory, 10 to the 500 universes or something, or a different number for a different theory, that have different physical properties, different physical laws. And that is the level 2. And these are the ones that basically come out from string theory, other theories called like loop quantum gravity, other ones. They have different classifications of the type of universes that would fit in, but each one has this vast set of universes with different physical laws. And this is the ones where I think where a lot of scientists stop. And in here, if they are universes, where are they? Where are they separated? And that's what we go into this different picture here. We have the individual universes that you see coming here, and then scientists sometimes use for the region between them the very scientific terms like space-time soup or space-time foam. Those are the two dominant terms used for this area between universes. And it's basically, again, like some form of space-time composite that is hard to define. And it itself is likely has more energy than the rest of any individual universe, and the more energy, the higher the cosmological constant, so the faster it's expanding. So this area between real universes, this space-time foam, is probably accelerating and growing faster than even any of the individual universes are. So that's what keeps the universes from just colliding with each other as they're growing. Although it is possible that these individual universes may have collided with each other early on when they were first formed and really close to each other. There was a paper that came out a couple of weeks ago suggesting more evidence of that. And these would be patterns. If our universe did collide with another one early on, then there would be patterns in the cosmic microwave background that would indicate that. There would be some spherical or circular patterns where the two universes may have overlapped. And there was another region that's under question right now. Back before the Planck measurements, there was some interesting areas, some suspicious areas in the CMB from the WMAP observations that were suggesting this. And they with Planck refining these areas even more, it turned out that it's unlikely, it's improbable that it was. But people were seriously looking into that. And now there is this other area that's still been, has not been dismissed as a possible collision area in a pattern that seems exceptionally low energy and empty. That might have been a region. But that was one type of evidence that would suggest it would be about the only way that we could actually confirm the existence of another universe in a multiverse, unless we can just prove inevitably that string theory or something is true from another independent means. There's also level 3 multiverses, and these were actually one of the earliest proposed. And these were proposed by a scientist who tried to consider quantum mechanics in terms of, who tried to consider cosmology in terms of quantum mechanics. How many of you have heard about about Schrodinger's cat? Everett proposed the same thing for universes. And what Hugh Everett proposed, and going back to Schrodinger's cat, was Schrodinger realized that quantum mechanics predicts what's known as a mixed state of things. That a quantum mechanical object can be both here and here at the same time, until we actually measure it and find it's only over here. So the original wave function has a composite, says it's both places, and then we actually take a measurement and see that it's here. And that sounds spooky, but it's actually been confirmed by experiment that that's true. And one of the ways this is done, it's been done testing both wave particles like photons and matter particles like electrons. You have an electron source here, you have a screen here, and you have a wall right here that has two slits in it, very narrow and fairly close. And you have this. You could fire either beams of electrons, or now it's even been shown to work with a single electron. You beam that electron towards the wall, and there's evidence that it actually passes through two doors and hits the screen, and these electrons interfere with each other, just like photons can. And there are lines in this back screen where the electrons have interacted positively, and there's an enhanced line. And then there's also darker lines where they interact negatively and sort of cancel each other out. And that works even when there's a single electron shot individually. If you're not measuring which door that electron goes through, it goes through both. But if you stop and measure it and have a detector at one door or the other, it only goes through one. So it all depends on how the observer detects the electron, whether it waits to detect it back here or right at the slits. So the electron actually does pass through both, or one, and only one, depending on what the observer acts, how it acts. And this relates and shows that there's nothing really independent of observer and the experiment itself, that we actually are part of the experiment. And so Schrodinger produced the idea of we have a quantum mechanical device that is either on or off. If it's on, it kills the cat in a box. If it's off, it lets it live. And the probability of either one is 50%. And you put this quantum cat in this quantum box, and until we open the door, the cat is going to be both alive and dead. We open the door, and it's either alive or dead, but not both. But until we actually see, the quantum cat is both. And so Everett theorized that this actually happens to us too, and that any time that there is a decision, either that we make or that nature makes, then the quantum state before that decision is all possibilities. And then once that decision is made, we end up going in one direction based on the decision we see. But that would be like flipping a dice. We would see the dice, it's going to land up anywhere from 1 to 6, but there's 6 different possibilities. I throw a dice, it lands up a 1. That's what we see in our universe. But it could have just as well landed up 2. And that would say that there's another, once it's been flipped and landed, there would be 6 different universes, with entire histories the same up to then, but different once at that branching point. And Hugh Everett theorized that quantum mechanics says that there's a multiverse in terms of choices, so that everything that exists keeps on branching into a new one, in a sense still here, not distance apart like in multiverse 1 or 2, or levels 1 or 2, but sort of the same here, but different here is because different realities. And that's become known as a level 3 multiverse. And the interesting thing is, if you consider initial conditions of the universe as like flipping an infinite-sided coin or something, each level 2 and level 1 universe can be explained can be equivalently described by level 3 universe. We just apply quantum mechanical choices to the different things that appear in a level 2, and you have everything there too. And so there's not really any difference. It's more a philosophical interpretation whether we're dealing with a level 1 or 2, level 2 with universes physically different, even different physical laws, versus a level 3 where they exist because of different choices in the physical laws in the breaking of them. One is physically separated, the other is philosophically separated. And the last type of multiverse that's come up is a level 4 multiverse. And this is what Tegmark has considered as the complete set of multiverses of multiverses. Each multiverse within a level 4 set is defined by a consistent mathematical structure. And so, like string theory would be a consistent mathematical structure. Loop quantum gravity would be a consistent mathematical structure, but it's a mathematical structure that in those two cases lead to different fundamental theories and different sets of embedded level 2 and 1 universes. And so he did this to basically say that this is basically the complete infinite multiverse of multiverses. And that's where it stops, because you can't have anything beyond that. And so when people are thinking about multiverses, they're usually, anything fits into one of these 3 theories. But on the science side, it's basically level 1, which likely describes our universe as an infinite in span. And then something like level 2 that explains its existence through a mathematical structure, and then also likely explains other universes too. And the other one, the other thing that's just the general idea of why we really think that a level 2 multiverse is likely is going back to the physics that caused our universe to exist. Why it became not just a Planck scale bubble, but expanded through an inflationary mode. The analogy that's used is to think of what we call it in a universe expanding through inflation into large size is nucleation. Our universe nucleated from this small space-time bubble. And I'm going to use the analogy to that of a pot of boiling water. First, it's unboiling. I fill a teapot with water, low temperature. I put it on a burner. It reaches 100 degrees. It starts boiling. How likely is it to only see one bubble form for the entire time you're looking at that kettle of water? I start 1 minute, one bubble. 2 minutes, no more. 3 minutes, a century. It's at 100 degrees, but only one bubble ever forms. That's going to get pretty unlikely. And it's the same thing with the physics. The physics that we're predicting, the physics, and it's not just one type of physics, but any type of potential, physical potential that produces our universe through the inflationary stage. It is inevitable to produce other universes like that too, to pop them out through an inflationary stage. They're not going to have, they're not guaranteed the same laws of physics. In fact, if it's something like underlying string theory or quantum gravity or something like that, each one should have a different randomly distributed set of physical laws based on whatever the underlying physical structure of the multiverse is. And that's how we get it. And that's just one of the, I think one of the best analogies that we can use why we really think that since our universe went through an inflationary stage, no matter what's true, string, loop, anything else, that there's likely some type of multiverse with other universes in it. It's unlikely to have just one pop out. And a little more than I was planning on talking, but I wanted to leave some time for questions, but I think I'll stop there then.
Time for questions.
Yes. Why don't you go first, then we'll go.
When it comes to universes colliding, they're not colliding in 3 dimensions, are they? And does gravity cause those collisions?
It's
I can't wrap my head around
gravity, no, but it's because they're expanding and they expand into each other. But they're also expanding and the space between them is too. So they would have some initial collisions and then away from each other. But what's really expanding is, it's not like planets within each or galaxies within each expanding, it's the space-time within each that expands.
Right. So it is. So we're talking just like 3-dimensional galaxies that get bigger.
Whatever the number of dimensions is.
Whatever.
Yeah, because like in string theory, it actually predicts that there are extra small dimensions too that could have been large, could have been on the same scale as the size of those universes when they collided. So that's what, yeah, we really don't know. But whatever number of dimensions overlapped. Yeah. Yeah. Yes.
So, if our universe exists in the space-time foam, right, and it has a higher energy density, what keeps it from collapsing our own space-time?
That's a good question. Basically, boundary surface laws.
Okay.
It's going to be ours has a surface to it. And that's sort of what you can think of overlapping too, and why you should expect circle or some spherical overlap.
Okay.
That's a very good question. Yes?
What about the theological implications of this? Do we think of other universes as other continents?
I think so. I think basically, I think it's an extension of the idea of extraterrestrial life in the universe. If we go beyond just the idea that God created life here, and I think first we would expand to the idea of God creating through a scientific process such as evolution, life elsewhere in the universe. It's not a far stretch to imagine life in another universe too. And the interesting thing is any life in our universe has to exist with the fundamental properties of atomic base, basically. But with vastly differing, fundamental laws, the life in other universes could be totally different. And that's something I didn't have time to get into, but there have been studies on that in terms of sort of distributions of physical laws in other universes and how that has to fit and how far away it would have to go to be able to produce something vastly different, from our life.
I could wait till later, but I can't resist asking this question now. I'll follow you here. One of the things that I find to be a difficult hang-up with string theory is that we know that the cosmological constant is about 10 to the minus 120 of what it could be in full range. String theory provides maybe a convenient answer for, there could be a whole vast set of them, and we happen to have the one that's just right. But there are theorists like David Gross and others that say, wait a minute, this is kind of dangerous to the whole pursuit of physics, which is looking for an explanation in terms of basic fundamental principles for why things are the way they are. Could conceivably we find in some supersymmetric theory a natural explanation for why the cosmological constant really does turn out to be 10 to the minus 120?
If we assume supersymmetry, which I think most of us do, and we really hope that supersymmetric particles will be found at CERN within the next 5 to 10 years, that proposes 10 to the minus 60. And in order for supersymmetry to exist, and what that means is that for every standard physical particle, which is known as a spin 1/2 fermion, that there is going to exist a spin 0 boson. And so, like, you have an electron, its supersymmetric electron is referred to as a selectron. The top quark has a stop quark. Quark has a quark has a squark partner. But they can't have exactly the same mass, or we would have already found it, and they would really mess up chemistry too. So, if you have exact supersymmetry, you have 0 cosmological constant. If you have broken supersymmetry, which means the particle partner exists, but the mass is different enough that we wouldn't have found it yet, then the predicted cosmological constant is 10 to the minus 60. So we're still off, even if we have supersymmetry and it's broken like we expect, we're still off by a factor of 10 to the 60. So that won't work. But in the end, there could be some explanation that comes about. It just, we have no idea yet how. And in the end, we do really have to be able to explain it somehow. And so right now, string is the only one that has really provided an explanation. But the interesting thing is, it really predicts that we would have, again, in these fundamental units, we would have cosmological constants or dark energy all the way from -1 to +1 in these increments of 10 to the minus 120. If it's negative, that corresponds to these universes that are imploding back. Something with a negative cosmological constant, it enhances gravity, and it's going to cause the universe to fold back in on itself. And these are short-lived things. If they expand like ours, it has to be a positive cosmological constant. But Steven Weinberg considered how large our cosmological constant could be and galaxies to form. And he worked on this in the mid-1980s, and he determined that for galaxies to form, the cosmological constant could not be larger than ours by a factor of 10. It could not be, ours is actually 10 to the minus 121, and it couldn't be larger than 10 to the minus 120. So ours is just within a factor of 10, the maximum that it could be for galaxies and therefore life to form too. And that was what the big question was, even way back then. Here's the physical limit that it could be. We're just near that, but we still expect it to be at least larger by a factor of 10 to the 60, if there's supersymmetry. And so that's the big question. Anyone here who could answer it, that's a guaranteed Nobel.
On this picture, what is the difference between the spherical universes and the one that comes to a point when they collapse on itself? Would it be like an anti?
That one on the end?
Yes.
Oh, just interesting design distinguishing something different.
Okay. If that did come back to a point, it was just a...
Oh, there are some. There are predictions, and I'm working on that with some colleagues right now, on possible cycles, even a universe like ours, that it could go, and there's possible variations of Einstein quantum gravity that can produce oscillating universes too, where they'll go out and it reaches a max and then collapses in on itself again and goes out. And you could use that to represent something like that. Okay.
How do you, I guess, handle some of the questions that you might get as far as tying in kind of your beliefs with the cosmos and then the Genesis
Like I said, I think the Genesis chapters 1 and 2, and a good part of Genesis itself, was based on people using their theological beliefs, or teaching their theological beliefs in the language of things at the time. And basically, this three-tier structure, as I was pointing out at the beginning, was not unique to Israel. It was something that was standard within the Mideast as a whole. And even a lot of the structure and the components of Genesis 1 and 2 were known to the other societies around the time in the Mideast. They were using what's sometimes referred to as stock things from the storeroom in describing Genesis 2 in particular in Adam and Eve. And Genesis 1 and 2 had distinct authors also, and they were written at separate times. And one was basically to show that Marduk was not God, but Yahweh was the true God. And the other was, and that was Genesis 1. Genesis 2 was basically written to show that Baal was not God, but Yahweh was the true God. And it goes back to the symbolism seen in each of these, of Genesis 1 and 2. So I think, Genesis and the Bible is meant as giving us spiritual advice. It's much of it is not. It's not a scientific treatise. I think we're misunderstanding a lot of the message of it if we try to take it as a scientific treatise. The true message and the true, spiritual value of it is misplaced then. Yes.
Is there some kind of observations that could be made to kind of validate string theory? And if so, what would those observations be?
The best one would be discovery of a supersymmetric particle. String theory is inevitably tied with supersymmetry, with a caveat on that. It is possible to form a string theory model that has a type of broken supersymmetry that's known, and other things, that the supersymmetric particles would have extremely high mass that could never be detected. But that's a very, very small percent of string models. So overall, if we don't find supersymmetric particles, then that will be an argument against string theory. At least it'll be an argument against 99.9% of the parameter space of string theory. There's still going to be a little left, and hardline string theorists might try to stay in that. I probably would give it up myself, but.
And along with that, how and where would they find that supersymmetric particle?
At CERN. That's one thing they're looking for. They're looking for evidence of supersymmetric particles. Now that the Higgs was found, that was the first thing. Find the Higgs. They did. The first evidence was appearing at Fermilab, and then it was confirmed at CERN. And now they're looking for supersymmetric particles. Evidence of grand unified theories would also help, but not as much as supersymmetric particles. And evidence of possible grand unified theories are coming up. There's some evidence right now of an extra W particle that looks like it's maybe right-handed instead of left-handed. And if that's true, would be an inevitable product of a grand unified theory. So that's not, if the W right-handed is found, it's not confirming grand unified theory, but it's giving support to it, and then that will give support to string theory too, because strings ought to generally have grand unified theories. But supersymmetry would be, there are other ways of having supersymmetry, but string theory predicts supersymmetry, so it's reverse argument.
All right, shall we thank our speaker again? We'd like you to come to dinner with us. We're going to go to the Corner Cafe. But before we break, I have someone very important to introduce. While our speaker is important to me, there's somebody more important to me that I have to introduce. That's my own mother. She's visiting from Kansas, so be sure to say hello to my mom.
You have to have a hug for that.